So welcome back. In this particular module, we're going to build off of what we did before, and we're going to be focused on comparing continuous values. And for this particular video, we are focused on two-group comparison. So this is going to be a treated versus a control. What I find interesting about continuous values is that these are things that sometimes we have to be kind of thoughtful about what distribution we're going to use. And we always have to be thoughtful, but it comes more into play here with with these kinds of data. So for instance, it's not uncommon for people to make a lot of assumptions that continuous data is going to always be normal, and that's certainly not true. There have been a lot of cases where I've seen continuous data that we can model in various different ways using various different types of distribution. So we always want to check that first. But unfortunately, in toxicology and pharmacology, and sometimes in biology in general, we don't have that many animals to deal with. You know, sometimes we're lucky to have 5, sometimes we're lucky to have 7, sometimes we only get 3. And when you have so few animals, it's hard to understand what the population distribution might actually be. And ultimately, if the samples that we have do not replicate the population distribution that we're interested in, our ability to do statistical inference is going to be really, really, really bad. So, unfortunately, we have a lot of things up against us in toxicology and pharmacology, but that is what it is. In this particular video, we're going to be doing an analysis of some rather crappy data. It's from the OpenTG Gates data set. And it's not crappy because it's from OpenTG Gates. OpenTG Gates, I'm very thankful that they make their data open. I'm not going to criticize them for that. It's more the issue, I grew up in omics, and there's this understanding within omics that an N of 3 is acceptable. And then people try to make inferences about these gene expression changes based on an N of 3. For those of you who weren't playing in omics back in the early 2000s, there was a huge debate as to why is it that this data isn't reproducible? What's going on? Why can't anybody ever reproduce it except for the really sensitive responses? And I think, a lot of it has to do with the fact that we're dealing with such small sample sizes. In a toxicogenomic study, if you have an N of 3, that's pretty good. I've seen lots of papers get published in the peer-reviewed literature with an N of 2. That's extremely unacceptable. But, in this particular case, we're going to go to into our analysis with the data that we have. What I like about this particular data set, though, is that we actually have a lot of vehicle data. And we're going to be using vehicle data from lots of different time points. And that, Bayesian analysis enables us to do that. And we're invoking a principle called exchangeability, which we'll talk about in a few minutes. So what's the setup here? So what we're doing is we're doing an analysis of carbon tetrachloride data. Carbon tetrachloride, I believe this is rat data. Rats were exposed to carbon tet for a certain period of time. And, if I performed the analysis I'm about to show you with a t-test, the p-value could be really significant, but you're going to see that what it suggests is that the carbon tetrachloride is hepatoprotective. That doesn't make any sense, but that's actually what some people have done, and they have tried to make that argument before. In fact, I reviewed a paper that did that, which is what inspired this example several years ago. I've been using this example again for several years. Really, what happens is when people don't actually understand what ALT is, they start making really silly assertions based on these really faulty inferences based on extremely small sample sizes. Okay, so what is ALT? ALT is alanine aminotransferase. It is a biomarker we use to see if there's hepatotoxicity. ALT resides in hepatocytes, and when the hepatocytes are dying due to whatever reason. Could be hepatitis, could be fatty liver, could be any number of things. But when the hepatocytes are undergoing cell death, they're going to release ALT into the bloodstream. And so we can measure this ALT. It goes up. Now, there's always going to be ALT floating around in the blood. And, even when you don't have liver toxicity. And that's why we have our vehicle controls, right? Our vehicle control is going to help us identify the fact that, hey, we've got this ALT floating around and, nothing bad's going on. So there's this normal amount. And that's what the vehicle control helps us identify, is what is that normal amount? Well, most toxicologists are going to tell you that really you're going to need to see ALT levels, 70 units, maybe even 100 units before we start to get a little bit concerned. So we have generally some idea clinically as to what a bad ALT level is, which is good. We don't have that in a lot of cases in toxicology. We need that in more cases, but we don't have it. So what inspired this example was I was reading a paper and somebody performed a frequentist test. It was a student's t-test actually of this particular data we're going to look at, and they said this is significant. Okay, so they saw this significant difference in this high dose carbon tetrachloride, and their argument, and this was carbon tetrachloride at 100 mg per kg at 9 hours, and their argument was, well, because the treatment level is lower than the vehicle, this carbon tetrachloride is actually hepatoprotective. So I've been studying, toxicology for quite a while, and I'm a toxicologist. I trained in it, and I've done risk assessments on lots of things. Never, ever in my life have I ever seen somebody make the argument that carbon tetrachloride is hepatoprotective. So that just kind of set off my spidey sense that, what? Where did this come from? No, 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 no. So let's look at this data you're using and let's see. Well, okay, so I looked at the data. It's like, yeah, that's what the data says, is that the treatment levels are lower than vehicle, but it certainly doesn't point to the fact that it's hepatoprotective. And what happened is, this is one of those cases where the vehicle measurements just happen to be kind of on the higher side of normal, and the treatment values just have to be on the lower side of normal. And so therefore the authors were able to conclude with this magnificent p-value that hey, the treatment actually created a lower level of ALT, which means it's hepatoprotective. No, as a liver tox person, I know that what that actually means is, no, the treatment is squarely within normal parameters. That's what this means, as is the vehicle. It's squarely within normal parameters. So there's nothing hepatoprotective about it. This is a case of there ain't nothing going on. That's what's happening. So anyway, that's what motivated me to create this example a few years ago. Yes, a few years ago. It was a while. And so we're using data that's found in this file that you can download, but I have it within the zip file for this particular lesson, so you can look at it and see it right there. Our objective is to answer the question, is 100 mg per kg carbon tetrachloride at 9 hours hepatotoxic compared to the vehicle? That's what we're trying to figure out. And so let's walk through the analysis. We're going to start off with the things that you always see me do at the beginning of every single analysis. And this is a coding convention that we normally do in software anyway. When we have to load libraries, we like to load them at the top. And that's what we're doing. When we have to set a seed, we set it at the top. When we have to set, little parameter thingies like this, to tell it to run a multi-core and to, save the rstand compilation, to disk, we put all that stuff at the top. So let's run it. This is all the stuff at the top. We ran it and it looks good. So what we're going to do this time that's a little different from what we did before is we're actually going to read in a text file. That's right. So I've got this text file here, and I'm going to use this command, or this function, I should say, read.table. And the first parameter into read.table is the file name. And you can see I've got the file name. Let's see here. It should actually be in here. There it is. OpenTG gates all attributes edt ratliver.txt. So I've got it right here. And then the next part that I'm telling it is this is a tab separated file, which means every record has a tab, and that's how the computer knows that this is, or how to load it, that every record is going to have a tab in between them. Okay, so the next part is this file has a header. So I tell header equals true. Once we read this in, and I'm just going to run this line right here. Let's just run just that line. I want you to see what this looks like. So I'm actually going to go over here. Okay, so there's all pathology. I'm going to open it up right there. And here you can see this big, large, ugly file, and it has lots of chemicals in it, right? I just saw acetaminophen. There we go. Got acetaminophen in here. You know, let's scroll down a little bit. Cyclophosphamide, methylpyrroline, you know, all kinds of good, fun stuff, right? So this is a huge file, huge, really big. Okay. We don't want all that data for this analysis. We don't need all that data for this particular analysis. We just want carbon tetrachloride, and that is the compound abbreviation right there. In order to find that, I did have to go through this file, but I did find it. So this next line here is a subset function, and the subset function says just subset. So just take a part of this object, all pathology, which is what I read the file into. And then this is the column name, compound.abbr. And I can, here, this will be fun. Call names. And we want all pathology, da, 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 da. This is all the column names in the all pathology object. And there's one in here called compound abbreviation. There it is, right there. And note, it has a dot at the end. It always has a dot at the end. Not always. Whenever they use an abbreviation, it appears that they put a dot. And that's cool. You need to make sure that what you put here is exactly as it looks here. It needs to be capitalized the same. It needs to have the same punctuation in the same places. If all you did was just do this, copy, and then came up here and did a paste, that would be cool. CCl4 again is the name of the compound that we're going to be working on. So we're going to run that line. And now I just want the controls. So I just have the CCl4 right now. Now somebody could be asking, well, couldn't you just do this all in one line? I could. I totally could. I could do this all in one line, and that would be cool. I didn't, but I could. You're right. Okay, so now let's look at this. CCl4 control. Okay, so that got me the CCl4 control. Note dose equals 0, right? And then I just want this particular column. Sweet, it works. I love when things work. Next, I want to get just the 9-hour, so the sacrifice time was 9-hour, 100 mg per kg data. So I have to specify all this stuff, right? So I got to tell it I want it from CCl4 pathology, that object, where the dose is 100 and sacria period, so sacrifice period, equals, again, 9 hours. And I'm just going to select this particular column, all right? Now then, you might remember when we looked at the control data, here, there's a bunch of NAs here. I want to get rid of those. NAs are not going to help me. In fact, in some cases, NAs will actually stop your program. So we're going to get rid of those. And what we're going to do is we're going to do we're going to do a little bit of our magic here. So CCL4 control is the object that I have, and it's a vector, right? So anytime I have things that are vectors, I can use these square brackets. I'm going to do something really magical. IsNA is another function built into R. IsNA is really cool. I'm going to type is.na, and that brings up the help file for isNA. What isNA does is it returns true anytime something is NA. So isNA CCL for control. And you can see false, 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 false. And it tells me everything's false. Well, I think I've already run it. Yeah, I did run it there. Let me get CCL4 again with all the NAs in it. Okay, so I got my NAs back, right? So now you see false, 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 true, 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 true. Okay? So what this line is going to do is it's going to say, okay, so take CCL4, and for every single element in CCL4, I'm going to then run the isNA, all right? So isNA CCL4. This exclamation point means not. So it's going to reverse falses into trues and trues into falses. So everywhere here where you see false, it's now going to be true. Everywhere you see true, it'll become false. This notation here within the square bracket, anytime I put something in the square bracket, if the value is true, it'll keep that particular entry in the vector. So what this is saying is this false is now true. Keep it, keep it, keep it, keep it, keep it, all the way down until I get to here. This true is now false. Because it's false, it says get rid of it, 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 get rid of it. So what I just did was I just got rid of every single one of the blocks that is NA. Now, someone could ask the question, but now wait a second. Those NAs are all at the end. Why couldn't you just subset this out and just say, okay, so from 1, 2, 3, 4, 5, 6, and just count how many there are here and just keep those and then just not keep those. I could do that. I could. It's better to get into the habit of doing it like this, though, because what if these NAs were actually spread throughout this vector? Do you really want to have to type all those numbers out of what to keep? This is much faster and it's much cleaner. So that's why we do it that way. So I run that, and now I look at CCL4 control. Voila, the NAs are gone. Isn't that great? So now we've got the data subset. We've got our treated data. We've got our control data. Now we can start analyzing it, all right? So like I said before, we're going to use the exchangeability rule in order to combine all the vehicles together. So what does exchangeability really mean? Well, it means that if data, that's the easiest way to put this. I try to write it out here. So if data are exchangeable, that means that there's essentially nothing different about them. You could mix them up and pull them out, and they're all basically the same kind of concept. So one way to think of it is, if I put all of the vehicle data into a vector, all of it, and I assign them index numbers, can I shuffle the index numbers that I assign to them and not lose any information? If so, then the data are exchangeable. Let me give you another example. Let's say like I had dose response data. And let's say like I said, okay, I've got dose response data and I'm going to put, all the low dose first, and then the middle dose, and then the high dose, okay? Now then, I'm going to index these in order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so I got 5 low, 5 medium, 5 high. I know that if I were to randomize the indexes, that I would no longer have these blocks, right? So if instead I were to say, okay, so I'm going to randomly assign my data into this vector such that I have no idea where the low and the high doses are, that's not exchangeable, okay? Because there is something different about them, and that difference is the dose that was used to create that data. With the vehicle data, I know, because this is ALT data, that vehicle should not be causing any toxicity. So if I know that vehicle is causing no toxicity, which based on the data I just looked at right here, these data all look like they're within the normal range. Because they're all within the normal range, these data are from different time points. That's cool. Because if I were to randomize the indexes for them, if I were to put them in by time point order and then randomize the indexes, it wouldn't change the overall, it wouldn't change how I work with this data within the analysis, if that makes sense. I know that vehicle is not causing hepatotoxicity. I know that vehicle is not increasing the ALT outside of the normal range. Therefore, they are exchangeable. Here's another example. If I had a big company that was doing a lot of in vitro studies, let's say, and my in vitro studies are all GLP, okay? My GLP process is validated. Sweet. What that means is that when I perform this in vitro assay on Monday and I do it again on Wednesday, my results should be reproducible. I can then combine together all that vehicle information that I have and not worry about a date effect. And because I don't have to worry about a date effect, then all my historical controls that I've ever done can also be used to help me build a more or a better vehicle distribution overall, to help me get a better sense as to what is happening within the assay when I do have treatments, right? So exchangeability is a very important concept. It's what helps us, uh, bring together data. And ultimately, especially with respect to vehicles, in many cases, vehicle tends to be very highly exchangeable. So, this is a net good thing. Here, it allows me to bring together all these vehicles to get a better sense of what that vehicle distribution is, because unfortunately, I only have an N of 3 on the treatment. That is really going to hurt me in the long run, because I will have questions about, well, how well can I infer this? But if my vehicle is really good, I can say, well, at least my vehicle's good. So, from a screening assay standpoint, this isn't so bad having an N of 3. But from a risk assessment standpoint, I would not feel comfortable using it. Okay, so that is exchangeability in a nutshell. So what this means for us is that we can actually exchange all the vehicle data. They're exchangeable, so we can bring them together as one whole data set, which is just absolutely awesome. So with that out of the way, you can see, there's ggplot2 there. This was me trying to test a few things out and moving some blocks around, so I'm going to clean this up as we go through. So here we've got vehicle DF, which is a data frame object that we're creating. We're using the data frame function. We're going to call the column control, and we're using CCL for control, which we just created. And you can see the contents of it there. It's a vector. So basically, we're converting this vector into a data frame so that we can use ggplot. Because again, ggplot2 requires data frames. Hopefully you said data frames. I'm sure you did. I'm positive at this point you said data frames. If you didn't, that's your little secret. Now you know it's data frames. Don't say vector. Don't say vector at all. Okay, so ggplot is taking in the vehicle DF object. AES is aesthetics, so how you want things to look. X is, because we're going to be doing histograms, going to be this control column right here within the data frame vehicle DF. Because I want a histogram, I got to tell it, I want histograms. And then you can play around with the number of bins in order to get the prettiness that you want. But here you go. Here's the histogram that I have for control. And you can see it, it kind of has this long tail over here. And this is really because of the number of bins I'm using. It'll look different if I were to change that, but it kind of looks like a Poisson distribution to me, because Poisson distributions tend to do this with this really long rightward tail. So I'm going to do some double checking. The key to know if you have a Poisson distribution is you have a mean and a variance that are equal. So we're going to see if that applies here. If my mean and variance are not equal, I know it's not Poisson. I know that I should not model it with a Poisson distribution. I could do a negative binomial. Now you might be saying, oh, wait, I thought you said this was continuous data and now you're talking about Poisson distributions, which are only with integers. What in the world is going on? My world makes no sense. I know. For some reason, when you look at this data, look at this data, look at this. These are whole numbers. I have no idea why. I never get integers back for my ALT values. So I'm a little, I mean, honestly, I scratch my head a little bit. Maybe they're rounded. I don't know. I have no idea. But I never get whole numbers for my ALTs. So I honestly don't know what's going on here. But anyway, so, I mean, if a Poisson distribution works, a Poisson distribution works, right? So, we're going to look at the mean and the variance. The mean and the variance? No, that's not close enough. This is not a Poisson distribution. This heavy tail could mean, well, actually, I see it right here. I'm looking at the variance. The variance is this number right here because it goes in order. This is the mean, variance, median, standard deviation. I'm looking at the variance right here. It's much larger than this mean, which means it's not a Poisson distribution. I could model this with a negative binomial distribution. Negative binomial distributions are really, really good for modeling things like a count data like you would with a Poisson distribution, except it's what we call over dispersed, which means that the variance is larger than the mean. I could do that. But I also looked at the median, and look at that median. Whoo-wee. That is really close to that mean. And when we have normal distributions, we normally have a mean and a median that are equal. So I mean, this is close enough. I could probably get away with modeling this control data using a normal distribution. Like I said, I could do a negative binomial. But in this case, I'm not going to. I am going to use a normal distribution. And that is why this works really well for the continuous situation, because we use normal distributions for continuous data a lot. Okay, so this just explains what I just told you. So let's model this vehicle data, which means we need to go to the stand file. All right, so here's the stand file. It's pretty cool. Comparing two groups, vehicle.stand. A lot of this should not be new to you. You've seen this before. This is the data block. This is the number of animals. This is going to be a vector of animal ALT data. So it is a vector of size n. N is the number of animals. Okay, makes sense. Everything's good so far. Parameters block. You probably remember that the parameters block is what the model is going to try to fit. It's going to try to find these values. Mu, which is our modeled mean value. It's also the name of a Pokemon. And then sigma, which is our modeled standard deviation. Now, our model is going to be the y values are normally follow normal distribution with mean mu that's being fit and some standard deviation sigma that's being fit. So we are fitting two parameters. We're going to use this generated quantities block in order to identify where our posterior predictive distribution is, and we're going to use that for model validation. Again, this is going to use the modeled mu and the modeled sigma, so the distributions of mu, the distribution for sigma, to try to come up with what is the predicted distribution for the actual y value. So we call that y tilde. And then we'll use that, we'll compare these new y values, these posterior predicted y values, to the original values to see, is this model in the ballpark or not? If it's not in the ballpark, then the model doesn't validate. If it's in the ballpark, then we're cooking with gas, right? So that's good. So let's run this, because you've seen all this before. This is nothing new to you. There it goes. It's running. Actually, right now it's compiling that stand file. So we will stand by as it compiles. That was a lame joke. Now it's running the model. There we go. And we can see we've got a mu value of 34.84. So that is the mean that it's estimating. We have a sigma of 6.79. Our y tilde is 34.74. And we can see that it's a distribution that goes from the 95% credible interval goes from 20.93 to 48.66. Pretty cool. So what we can do is we can go back. Let's just scroll up really quick. Let's look at these control values. Yeah, it's certainly in the ballpark, isn't it? That seems highly reasonable, actually. But I'm not content with just eyeballing things. I actually want to look at this a little bit more visually. So I'm going to extract the y tilde values from the vehicle fit that Stan did. So I'm using extract. I'm going to create a new data frame because I want to plot this using ggplot. And so I'm creating a column called data, which has my y tilde values and CCL4 controls, and then a labels column as well. And then it's going to label all of the y tilde values as predicted and labeled all the observed values from CCL4 control as observed. And there you go. ggplot again, we're doing histograms. Nothing really cool here. I mean, fill's gonna be labels and color's gonna be labels. You've seen that before. So let's run all that. Bada bing, bada boom. There we go. Wow. Well, that's just darn fascinating, isn't it? It looks like the observed values are hiding really behind the predicted values, which would say that this is a really well validated model. Looks good to me. So they overlap extremely well. So now we're going to go to our treated model. Let's just run this to see what we're working with here. So because I see our data in this kind of a format, I know I ain't dealing with vectors here. I'm dealing with something else. So if I want to find out what I'm actually dealing with, I'll type class CCL4. Yep, that one. It's a data frame. Oh, interesting. So we're going to have to remember this when we get, oh, and hey, I didn't even notice it there. Right there, it tells me what it is. It tells me it's a data frame. So we're going to have to be careful when we go to use this because it's not a vector. So I'll show you how we're going to deal with that in a little bit. So like I said, one of the things we see here is we got an N of 3, and they're pretty tight. That's pretty cool for an N of 3. We don't normally see them quite so tight when we have 3 samples from a population distribution. So that's cool. It's probably going to be rather easy for us to model. Again, my chief concern is the fact that this is such a tiny sample. Is it really going to be representative of the population? Generally, it's not. So I'm going to have very serious reservations with any inference we draw from this study, but we're going to do our best and see what we can do. Okay, so now we're going to go do the stand modeling. What does that mean? Let's look at the file. Holy cow, this is different. This is much different. What on earth is going on here, you might be asking? Well, let's look. Data, that looks the same. Parameters, that looks the same. There it is. The model's different. Now you might be saying, now wait a second here. Why in the world did you have to put this in? Why are you setting flat priors for this model, whereas over here you didn't set flat priors? Well, it's because of the way that the sampler works. So the sampler has certain places where it's going to start looking for values. And when I ran this without the priors being set right here, it used a set of default priors, which are not what I used here. And it came up with some really strange results. I mean, really strange. And you can run it through this file here, and you can see what I'm talking about. You'll get a warning that you're going to have some transitions that didn't converge. And I had like 500 something transitions that didn't converge. That, when I started looking at the results, it made very clear that no, this was a horrible model, and no, it did not validate well at all. When you have that, usually the first thing you do to fix it is to give it a better sense of where the priors are. And so I'm still using a flat uninformative prior, but I'm saying, mu is going to be somewhere between 0 and 100. I know that because I know how ALT works. Okay. If you don't know anything about ALT and you want to set a prior, you need to go talk to somebody who knows about this. So this is where having a toxicology background really helps, because if you are a toxicologist and you know ALT, you know that the mean probably is going to be within this range, especially given the fact that we're dealing with data that is over here, right? I probably didn't even make this 100. I could have made this 50, right? But what this does is this constrains the model from going way out into left field and sampling ridiculous numbers that are like, something times 10 to the seventh and crazy stuff like that. You don't want that. Okay, that's really the only major difference. This is the model again. So we're going to go back over here. We're going to save. All right, you ready? Let's run this. And again, there's a hash mismatch for some reason, so it's recompiling. So we're going to just wait for that. I'm not going to say the silly joke again. You can, though. Feel free. Feel free to use this. Use that joke with your friends and family. I'm sure they'll really appreciate it, as you're not coming to the dinner table because you're running stand models. That wouldn't be something I've ever done, would it? Aha! Okay, so I'm still having some divergent transitions after warm-up. I haven't, that's kind of interesting. Let's see if the model if the model is still validating well, then we can normally just say, yeah, that's cool. And let's see here, the mean's 27, the tilde is 27. We are getting some wonkiness out here. So what I'm going to do, you're going to see me try to troubleshoot this in real time. 100, not acceptable. What do I actually think the prior for this particular treatment is going to be? Probably closer to, oops, wrong number. This would be acceptable. In terms of sigma, the sigma really shouldn't be that large. It might be even here. So let's save that. And let's run this again. Let's see what happens. You gotta love doing trainings with live code, because you never know what's going to happen. It's like working with wild animals, and you're probably thinking, well, didn't you run this earlier? I did run it earlier, but I didn't have the seed set, so shame on me, right? Hey, all right, I was hoping this would happen. Now you're probably thinking, why in the world would you be happy that your session aborted? Because it helps me help you, because this is going to happen. Sometimes, for some reason, some kind of error happens. I don't know what's causing it. This is normal. I know. You're thinking, this is normal? This is good? This is okay? No, this is weird. That's what this is. Okay, so we're going to come back here. Da-da-da-da. This is not the one I want, is it? Let's open up my projects. Comparing two groups. No. There we go. That looks much better, doesn't it? So we gotta start this all over again, but don't worry, I'm not gonna talk you through all of it because you already seen all this. I'm getting a bunch of package warnings, and that's because certain packages were built under a different version of R, and that's okay. I haven't checked recently if Stan is still having the issues that it was with the newer version of R. I need to check into that. Gonna run this. This is the vehicle. And you can see it's recompiling it in order to avoid crashing R, because last time R crashed. So it's trying to recompile it so it doesn't make that mistake. We see it just completed while I was taking a drink. That was good timing. Okay, so we've already done all that. We're going to do this. Looks pretty good, pretty happy with that. Gonna run this. Yep. Run this. Let's see what happens. It's gonna recompile the stand again to avoid crashing R. That's what it's telling me right here. So we're gonna wait just a little bit. And thankfully it's usually pretty quick. It looks like I've got one worker started, got another worker started. Okay, so when I when I tried to fix it, I just made it worse, didn't I? I have 1,811 divergent transitions after warm up. So there's a couple things I could do. One of the easier ones is going to be, let's see here if I can pull this up. I can change the adapt delta, which is actually, if I, here, you get to see some magic. I'm going to go here, not this one. I may have to go into a different directory. I'm going to have to go into a different directory. No. I might have it here. No, I don't. Let me go back to a different directory. So there's a couple of options that we can set, and one of them is the adapt delta. Okay, so we're going to set control adapt delta, and I'm going to set this up kind of high. What this does is it forces Stan to spend a little bit more time doing a little bit better job of walking through the sample space. So we can see here, it's doing kind of a better job. And let me treated. So we're telling it, for the most part, it's probably in this neighborhood here. For sigma, we're telling it it's within this neighborhood here, 0 to 10. I'm trying to think, what would the population for that be like? And 10 is probably a pretty good estimation. I might just take that up a little bit, but I don't think that's going to matter a whole lot. And if I continue to have this issue with the divergent transitions, I'll need to think about, is this really something I want to deal with, or is this not something I want to deal with? In other words, is this something where it looks like the model is not validating well, or is this something where maybe just the tails are going to be an issue? And you can look at the pairs plot to try to see as well what's going on. So I'll try to pull that up because this isn't the most complicated model in the world. So let's see if we can pull up a pairs plot. This will just take a second for it to load up. It's saying 802 divergent transitions. So what's happening, oh yeah, look at all those little red dots. So here within mu by sigma, we can see we're getting the divergent transitions all over the place across all the values of mu and across all values of sigma. And that's not great. Y tilde, we're seeing that we're getting it all over the place. So basically what's happening is we've got divergent transitions all over the place, which is numbers that are not exactly great, and they are diverging from some of the other estimates. And so what happens is we end up getting kind of an explosion of values, which ends up, kind of hurting what we're trying to find. Usually it shows up in the tails. So here you can see where mu is in the middle and where sigma is really low. That's where most of our data is concentrated. And then we got some scatter out here as well. So in this particular case, it's kind of hard to figure out what exactly the issue is and how exactly to solve it. So instead, what we're going to do is we're going to look at, okay, let's look at this. Let's look at the y tilde value. This distribution is certainly much larger than what we're finding with the 3 samples. And to be honest with you, I don't really have too many problems. Based on this, what I'm seeing, I'm pretty sure I would have to run an analysis, which I'm not going to do right now, um, to be more certain, but I'm pretty sure what we're seeing is reflective of low sample sizes. When I run stand with low sample sizes, this happens a lot where I have a lot of divergent transitions. Now remember, I have 802 divergent transitions over 15,000 samplings. So what that means, that's why I'm saying usually we see these kinds of things in the tails, not necessarily in the center. So it doesn't really concern me that much, especially since, here we go, especially since this, distribution is reasonable, given the fact that, I mean, come on, we only have an N of 3. I could see this being a very realistic population distribution. So when we see this warning about divergent transitions, we do need to stop and think about it. Sometimes it's not a problem, sometimes it is. In this particular case, I don't really feel that it's a problem. The model is still working very well for me, so I'm going to move on. And again, I think this is mostly because of an NF3 issue. So now we're going to use our vehicle mu data. So this is what the sampler thinks the mean for the vehicle is, as well as the treated mu, what the sampler thinks the treated mean is. And we're going to calculate our difference distro right here. So let's run that, and then we're going to plot, or sorry, we're going to make a histogram of the difference distribution. Sometimes when you're running in the R notebook environment, you have to run it twice in order to get the histogram to actually pop up. And here you can see, here we've got this difference distribution. It's definitely to the left of 0. So, we've got that going on, right? And now what we're going to do, well, here, we can do an analysis just based off this difference distribution. Treated is not greater than vehicle in this particular case, so we know we don't have toxicity going on. You cannot really use ALT to say much about hepatoprotectiveness with the study design that we have. In order to demonstrate hepatoprotection, you would have to treat with something that you know is going to cause hepatotoxicity and co-treat with something that you think is going to protect. That's the way that you would prove this. You wouldn't prove it by taking something that doesn't cause hepatotoxicity and then get no hepatotoxicity. That just doesn't work that way. So the ALT level in the treated group is likely lower than in the vehicle. That's not really surprising. We kind of knew that was what was going to happen anyway. So there's not really much point in calculating this 95% highest density interval, but we're going to do it just mostly for practice. The other thing that we're going to have to do is we're going to have to calculate as well the rope. So remember, the rope is the region of practical equivalence, and it is, basically the region where we feel we have no biological difference going on here. There's a couple ways of establishing the rope. I could use what I know about biology, which is to say, if it's less than 70, it's probably not real. It's probably not hepatotoxic. The other way I could go, and I'm doing it this way mostly to show you how to calculate it using the vehicle data. The other way to do this is to use the vehicle data. So what we're going to do is we're going to do some fancy math. We're going to calculate the highest density interval, and we're going to use to calculate the highest density interval on the y tilde. Remember, this is the posterior predicted values. These are the predicted values for y, or for ALT, that we think we're going to have in the vehicles. And I'm going to take number 2. So let me just go through this really quick so you can see exactly how I got to this particular notation. So the HDI is going to spit out these two numbers, a lower and an upper. This is a fancy printed vector or object, but what the vector is, if I just take this object here, the vector is actually just these two numbers, the lower and the upper. The first position in the vector is the lower, the second position is the upper. So I'm going to take the upper from the HDI, and then I'm going to subtract the mean. What that does is that tells me how many units past the mean do I have to be in order to have the upper range of my rope. I'm going to do the same thing except with the lower, and again subtract that from the mean to get the lower end. Okay, so let's run that. And we can see that my upper end is looking like 14.3, and my lower end is looking like negative 13.3. So that's what we have here. Doesn't need to be symmetrical. Typically isn't symmetrical, so that's not surprising. So now we ask if the difference distro. Now, okay, let me back up. So what we're saying is that 14.3 units greater than the mean is where we're going to put the one end of the rope, and then 13.3 lower than the mean is where we're going to put the other end of the rope. This is not exactly biologically driven. This, in this case, is data driven. This is based on the vehicle distribution. Like I said, I could do a data-driven one. I'd have to go back and reread the literature to see where we normally put the cutoff for this particular strain of rat. My gut instinct is that it's around 70, but this will work just as well. Well, pretty well, anyway. And it's very justifiable. So now we're going to ask, what is the difference distro 95% highest density interval? And so you can see here now is, I'll have to update this because I got a slightly different result this time. 14.4 to, man, that's really interesting, 0.45. This is, in this case, actually, it's all within the rope. In my other example, it was not all within the rope. Most of it certainly is. So we can definitely conclude that this dose of CCl4 is not toxic. Definitely. And let me get rid of some of these things here. And, you know, again, I changed what these values were. So if I moved them back to where I had them before, I probably would have replicated this result. But you can see the difference that, you know, that changing these priors makes it. The priors do have an impact on things. So anyway, we can definitely conclude that this dose of CCl4 is not toxic compared to vehicle with respect to ALT. That's for sure. So some other things that we can do is if you actually wanted to graphically show what we're just doing here by eyeball, you can do that. You can graphically show it. And so let you make sure I'm not hard coding anything. I'm not. Yeah, so this is, here you go. This is the rope. Right here. This is the rope. And you can see that most of that distribution, and you know, based on what it's saying here, the 95% highest density interval of this distribution is clearly within the rope. So it is not significant. So what I did here to draw these vertical lines on the histogram is you do everything as normal, right? Geome histogram, but then you use geome V line. And you tell where the x-intercept is. And the x-intercept is going to be on those rope values that we calculated up here, right? So I just copied these down here, and there you go. That creates that. But you want to do something even prettier. You do this. Now what I have is I have a slightly shaded in area for the rope so that now you can see even clearer. Oh, this part right here is the rope. Okay. The way I did that is, again, geome V line, there's the histogram, but then I used this annotate function, which is really a lot of fun. I told it I want a rectangle. I told it where the min value is for the lines, where the max value is, where the y min and y max are, and then I told it 0.2 for an alpha. That's the transparency level. And there you go. I really like how this works and how this looks. So I do tend to use this particular arrangement in order to make this. So I think the shading just makes the rope a little bit more apparent, and it makes it a little bit easier to see that, yeah, really, no, this really isn't the thing. The treatment really is not different from the vehicle, and that's really the bottom line. The treatment group isn't showing any signs of liver toxicity, period. End of story. Anyway, thanks for tuning in. Thanks for being part of the lesson here. You got to see me do some real world debugging, which I usually spare you from. But most importantly, I was happy that you're able to see, what happens when R crashes. How do you handle that? And more importantly, I'm glad we were able to talk about these divergent transitions. As you could see, I was not prepared for the divergent transitions. I was not expecting that to happen. It did. Cool. Um, and hopefully you can see the mind, the thought process going through of, okay, I've got divergent transitions. Normally, what that means, and I guess I didn't tell you some of the other things that I was eyeballing that I should have talked about. When you get these divergent transitions, there are things you want to look at. You want to look at the n effective. The n effective needs to be pretty large. If this r hat is not 1, then these divergent transitions are probably making a negative impact on your model. So my r hats are all 1. My n effectives are large. They're in the thousands. So I feel pretty good about that. When I was looking at this, it's an n of 3. Being able to get anything decent off of an n of 3, it's just darn near impossible. The fact that this was the best standard deviation that the model could come up with, and then of course this is what I'm going to have as a result of this standard deviation and this mean. This is what I would expect. So overall, this isn't bad. The model's very well validated. Really, I think, again, a lot of this problem comes down to the fact that we really are just using a really small data set, and it's extremely tight. And that just doesn't happen, right? So to me, again, what we're seeing here, when this data was analyzed through a frequentist approach that had such a small n, that was just highly inappropriate. And that p-value, of course you're going to see that p-value because the data were tight, but that's not a good, that data for the treated is not a good representation of the population. And as a result, I really don't feel very good about the inference coming out of this. Now, when I look at this in terms of realistic values for, what we could be seeing, this to me looks like a realistic population value. I could get behind this, but still, because I have so few samples, I have a lot of concerns about this. So is this ready for a risk assessment? Oh gosh, no. I have very little confidence in this database just solely on the sample size. Could I use this for screening purposes? Yeah, I'd feel a lot more comfortable using this for screening and prioritization of chemicals. So like if this chemical wasn't carbon tetrachloride, but it was something that I knew absolutely nothing about, it was a new chemical that my company was dreaming up, I would feel comfortable using this for a screening and prioritization to say, we're going to need more data, but right now this doesn't look to have much hepatotoxic liability with respect to the ALT. I'd want to see what the AST shows me. I'd want to see some other things. I'd want to see what's happening with respect to a fatty liver type assay, something like that. But right now, all chemicals being equal, this one it probably is not showing much with respect to a hepatotoxic liability. And so from a screening and prioritization standpoint, yeah, I'm okay with this data. It's not what I like. I'm okay with it. But, we're talking early development here. If this chemical was not in early development, if this chemical was closer to production, this we can't use this data. This is highly inappropriate, and we can't draw those inferences. So that's my thought process. That's how I go through this. And so anyway, those are some of the parting thoughts I wanted to leave you with respect to this. And again, you've got a lot of code here that can help you do a lot of really cool things as you come up with, come against other kinds of data and data sets where you may have just a 2-group comparison. So remember, this is what you would do instead of a student's t-test. All right. Thanks, everyone. And thanks for sticking with me, and we'll see you on the other side.